Monday, we finalized single cycle data path, and then we transitioned to pipelining. But before we continue talking about pipeline data path, I indicated that we will do some practice here in class for different type of instructions, navigating through the single cycle data path. So I'll try my best to highlight these lines and annotate it, so that way you fully understand what happens when the instruction goes through the processor. Um, yeah, and again, if you have any questions, just please let me know, and then I'll try my best to keep this highlighting as best as possible. My recommendation is do have a digital copy or physical copy of this data path. As you can see, I already wrote the instruction that we're looking at, which is an add instruction. So this will be an example for all R type instructions that we will see, but we're using add instructions so you can see a real example. Again, as I'm sharing my screen right now, I'm not able to see the chat. So if you do have a question, just raise your hand and I'll be able to see so you can ask your question. Okay. It's a highlighter. So the first thing that we need to understand here is what is it that we need to look at, right? So for an RTAP instruction, I gave you the blueprint for an RTAP instruction. So I'm showing you this table because, again, this table is important to know what are going to be the bits for an LU up and also for an LU control. And also I'm showing you this again, this pretty much the format of the instructions, because the breakdown of how you can see the RD, where it's located, the RS1, RS2, and so on, and the opcode. These bit representations here, 0 to 6 and 7 to 11, it gives you an idea where things are going to be traveling through the data path. So again, if we look at the data path here, you see 0 to 6, right? So you get 0 to 6 here. What do we know about 0 to 6? That's the opcode representation of all of the instructions. So that's why we're going to start with our type instruction, and then we go from there. So again, if you're still not familiar with these formats, it's good that you get familiar, but also this process will help you understand better these formats and why it's constructed this way. So let's start with the highlighting real quick. So again, if you're not able to see, if you have any questions, just please let me know. So what do we know? That the first stage is fetching the instructions. So program counter starts here, so we go from here. So we have we're working with an add instruction. We have an X9, which we know that's going to be our RD. X28, that's going to be our RS1, and X29 is our RS2. So we go through here, but there's no multiplexer here stopping the instruction, this from going all the way up here. Again, I'm actually left-handed and using a mouse with my right hand. So this is gonna be interesting. So we go through here, and it goes through here. Typically, this part of the top, I do that at the end, but I wanted to show you how that gets highlighted. I'm not going to highlight this line here for this example. Why not? Because we're not using a branch instruction, right? So we're using an add instruction. We know this information will not be needed for this add hardware here because there's no branch instruction that we're working with. So we go here, we read the address from instruction memory. So that means that we fetch the instruction, and then we go from here, and then all these parts here are going at the same time. What do we know about add instruction? We need an RS1, we need an RS2, and then we need an RD as well. So that means this is going to be highlighted. This is going to be highlighted as well. And this is going to be highlighted. We're going to write back to register, right? So that all of that's going to be highlighted. Okay. So we go through here, and this part here also gets highlighted, right? So, but then if you see here, there's an emitter generator that goes towards this LU, or it goes all the way to the top for this shift left. What do we know? We don't need that, so we're gonna bypass that. Go through this instruction part here, and go to the LU control. Okay, so we're going to be reading register 1. So annotate. I will do that later because it's easier to do that by just adding the text than me actually trying to write it with the mouse. But what does a good here goes the opcode right through the control. So if you want to write OP here, that's fine. Then for the read register 1 here, that's going to be our X28. X29 goes through the read register 2, and then our write register is going to be our X9, right? Because that's our RD. Then, of course, it is the rest is pretty much any functions are going to go through here and so on. That's pretty much the function go through here because we don't need to go through the immediate generator for an offset going to the LU or the shift left here. Okay. Then after, so this part here, we read the data 1 from read register 1. So we're going to highlight this part here. And we're going to read the data 2 from read register 2. So that's going to go through here. This multiplex is going to be selected as 0. And then it's going to go through here. So why is that 0? This line that through the mirror generator, if you see here, this bus also goes and feed that to this multiplexer. There's no input going to this multiplexer here. And we know for an RTAP instruction, we don't have an offset. We don't have, we're not going through, so there's no, doesn't need to go through the LU. So that's why we're getting an input from the read data 2 here from RS2. So that's why that 0 is selected for this multiplexer. Then that value is stored in X29, goes through this multiplexer, so that now X28 and the value of X28 and the value of X29 is sitting at the LU stage. So we're now at the execution stage that gets added, right? So even if it's 1 plus 2, then the output is 3. So we have here this part here that goes to direct data memory, or it bypass data memory. What do we know about R types? It doesn't access data memory, right? So we're going to highlight that part here, skip that part here, and then we're going to highlight all the way over here, bypass memory, and then we're going to select 0 because that's where the data is receiving it from this input of 0, the multiplexer. The 1 would be because the data is coming from memory. And then, of course, we're going to write back that to register, which is the last stage. Yeah. Okay, so we know that program counter is going to be PC plus 4 because it is 4 here, it's 4 bytes. It's going to be added here, so the 0. And then, of course, that's just going to go back to and that's going to fetch the so they can update the piece the address for that as it goes to the next instruction. Right, so if we were in instruction number 1, then it's going to go into instruction number 2. Any questions on this data path, or do you think we're missing anything in terms of the highlighting? Yes, Trace, go ahead.
So is everything from the instruction memory block to registers all step 2?
You're referring to stage 2, right? Yeah, yes. So this part here is your decoding. So this where it's happening here at the register stage, that's all decoding. So we'll have the fetching here, decoding happening here. Why the decoding? Because we're getting RS1, RS2 going through here. It reads that register, then it reads the data within that register. So all the decoding is happening there. And the execution is happening at the LU stage right here. Accessing memory, if we are going to be accessing memory, is of course is happening at the data memory stage, and write back is this piece at the end, which is very small. Any other questions on this? Okay, so let's do a quick annotation here. Actually, yes, I want to keep that part type of annotation. No, so I want to keep that. So I see you can still see my screen. So I'm going to do some text boxes here. I think it's easier to use these ones over. So we're going to use X9 because our RD, so that's going to go right here. So when you're annotating these things, make sure that you are providing this. So RS2 is going to be our X29. right there. So you can see it travels through, and then of course, you know that this is gonna be our X28, which is right here. Okay, and then of course it travels through free data. If we have the actual value, I'm just gonna say that X28 is holding the value of 1, and then the value of, the ratio of X29 is holding the value of 2. So this 2 goes through here, that gets added, and then we should be getting a 3 output that is supposed to be right here. So it'd be 3, and that 3, of course, carrying back all the way to DRD, so that when it says write data, this 3 should also be going on here. And then, of course, the final value of X9 be holding 3. Something else, of course, this is going to be PC plus 4. Just always remember that. So this is going to become PC plus 4 right here on the top. Okay. Let's look at our control values. Can somebody tell me, you can just, what's going to be the value of branch for this instruction? So that's going to be 0, right? So I'm going to change that. That's going to be 0. Why? Because we're not working with a branch instruction. We're working at RTAP instruction. So how about mem read? That's going to be also 0. Why? Because let's see. That's also going to be 0 because we're not reading from memory. And then we have memory to register, meaning that are we sending any data from memory to register? No, we're not doing that. Again, we are not accessing memory. Then the LU up, can somebody tell me what the LU up is going to be for add instruction? Remember, that's going to be 2 bits. I gave you that table. Make sure you look at it. That's going to be 1, 0, right? Which do not forget that also talks to control. This 1, 0 goes to control all the way over here. And our control value is 0, 0, 1, 0. Again, look at the table. Memory write, again, that's going to be also 0 because we're not writing to memory here. How about our LU source? Is that going to be a 1 or a 0? Getting this notification here.
Wait, would it be a 1? Yeah, or for reg write, would it be 1?
Yes, that would be a 1 for reg write for the last one. Because we're running back to register, so that means that it's going to be a reg write. That's right here, that's a 1. LU source is a 0. Why? Because this LU source is connected to this multiplexer, and we're selecting 0 here because the RS2 is the one getting us an input. So that's why that's LU source is 0. Again, this 1 and 2 here, as a reminder, if you read data, we're assuming that X28, write in your notes, X28 is holding the value of 1, and X29 is holding the value of 0. I'm sorry, of 2. So if that's being added in the LU, there's an add function there. So that means that the output is going to be a 3. Okay. So, and then of course, X9 is going to be holding the value of 3 in this case. Questions? Any final questions about our add instruction that we have here? So if I ask you to, I gave you this single cycle data path and I give you an add instruction, this is pretty much what's expected of how to annotate and how to trace, how to highlight each of these buses. Something also, nobody mentioned this, you have reminded me this, so don't forget, our opcode goes through here. I'm just gonna write OP for opcode. Goes to control.
I have a question. I'm still a little bit confused, at least what the multiplexers do in determining how it gets through the pipeline. So I understand that 1 and 2 is when it goes to the ALU to get a return of 3, but how does the multiplexer play a part in that?
Yeah, so good question. So typically when you have two inputs that's going to the same bus of the ALU. So if you imagine this multiplexer wouldn't be here, there wouldn't be not anything pretty much choosing or stopping the second potential input going through there. So how the multiplexer here by choosing the 0, it helps the path of this value going through the LU. If you look at this multiplexer on top here, when you have a branch instruction, you're going to have this multiplexer is going to have two different inputs, PC plus 4, and the value that to be able to the PC plus the offset to be able to calculate then where we're going to be branching to, right? So now because you're going to have 0 or 1, for this to be selected as 1, this AND gate needs to be activated to be able to select the input coming from the 1 instead of the 0. If we don't have this multiplexer here, then there's nothing controlling or the path of the PC plus 4 versus the calculation of PC plus the offset to be able to branch, right? So that's why the multiplexer is needed when you have multiple inputs going to the same path. See, 1, 2 inputs going to the same path here. So that's when you need a multiplexer. Does that answer your question?
I see. So it makes the appropriate decision based on what type of format we use, instruction format.
That part of it, yes. So that's why you have an LU source here helping this multiplexer to select, okay, are we getting this read data from here to multiplexer? And then again here, also this multiplexer after data memory, it has two inputs. One straight from the LU, another one from memory. So every time you have two inputs going to the same path, then you need a multiplexer to be able to decide which is the correct value that's going to go through.
I gotcha. Thank you.
No problem. Any other questions?
Yeah. ALU op, should that be 0, 1, 0 instead? Or on the slide it says 0, 1, 0.
No, go back by this table.
Oh, okay.
Yeah. So you see 1, 0, and then the LU control is 0, 0, 1, 0.
Okay.
Any other questions?
Yeah, so we would have to memorize like the ALU op for each of the instructions to be able to write in the control for like annotations.
Yeah, pretty much. Yeah. So for the LU op, knowing that's gonna be 1, 0 and 0, 0, 1, 0, and the more you do this, right, the more practice it, the better. Okay. All right. So let's look at a store instruction. We put this again here, so we can use the highlighter method. All right. So what do we know about store instruction? We have an offset. We have a store. We have a RS2 in this case. I'm sorry, an RS. So we have also here two RSs pretty much, but they just have two different purposes, right? The goal is to store the value into memory, right? So where do we start? PC here, that's going to be the same. So I'm going to leave the highlighting towards the end. It's pretty much going to be the same highlighting for the top as the RTAP instruction. So here we're going to highlight this part here. We know that opcode goes here. Then our RS1 with RS2. How about RD? Did we highlight that one?
No RD.
Okay, no RD, right? Because we don't highlight this one because this, again, the store instruction does not have an RD in this case. Okay, how about here? What's happening? I stop here. Do we go down or do we go through the image generator?
Go through the immediate generator.
Okay, so if we go through the immediate generator here, right? So that's gonna be our offset. It's gonna be traveling through here. So this is gonna be highlighted. And then our R1 is this one is gonna be selected instead of the 0, right? Now, again, if you're saying that we don't have an RD, but we have an RS1 and we also have an RS2, but we just selected here the offset to go through here, right? Through the multiplexer. What happened to this read data 2? Okay, so again, yeah, go ahead.
So yeah. So with the multiplexer here, the data for read register 2, I'm assuming like the circuitry would, assuming that the circuitry doesn't get like turned off, there could be an output for like read data 2, but it's not going to go through the multiplexer, so it's just going to be nothing and just going to dissipate onto the ether, and the instruction's going to go through, or the immediate's just going to go through.
Okay.
So,
Yes. So in this case, pretty much you have the offset going through here, so that because we need to have the offset and the base address goes through here through the RS1, right? So we got register 1, we got a read data 1, so that means our X29 is going to go through here, our offset is going to go through here, and then the offset plus the value of the base address is going to be added here. So, and that's going to become go to data memory and become your target address. That is going to be read, right? But what's happening? This address, because it's a store instruction, we're telling data memory, we're going to write back a value into this address. So this read data 2 here, right? So it's not going to go to this multiplexer, but it's going to go down. That's why we have this line here. And it's going to go straight to data memory. So the value of a storing X9, let's say it's holding 3, it's going to write that data into data memory. Right there. So that's how it plays out. So again, offset goes through here to this multiplexer. 1 is selected, goes to the LU, great. Base address goes through the LU. So now we know the target address that we're going to be writing the value to. And we're going to take the value of holding X9, and we're going to send that directly to the data into data memory, because now we know the address that's going to be sent to. So again, don't forget to highlight the top here. It's going to take me time if I do that too fast. So do that yourself. I'm not going to do the whole thing. Again, highlight all of these here. Select this 0. Highlight that all the way to the back. It's going to be exactly the same as the RTAP instruction. Okay. Any questions about this highlighting for a store instruction?
Yes,
Mhm.
I do. So again, for the read data, right? We're assuming read data 2 goes directly into write data,
Right.
because this is a store.
Right.
So is it actually physically engineered the circuit to head to write data, or is it also touching the multiplexer as well?
So all these rules, yeah. So all these rules are already hardwired into the data path. So that's why when the opcode goes to control, it pretty much tells the data path what part of the hardware is going to be used. Because we know the store instruction needs or it has an offset, and it's going to be receiving an input from offset to this multiplexer, going to the LU. That's why this read data 2, that's why it has 2 buses, right? So it's going straight to the multiplexer, but it's already receiving an input there. And the goal is not to add the value of the value within the raster 2, is to use that value directly into memory. Yeah, so
Gotcha.
that's why you have
Okay.
that line here and here. Yeah.
Okay, thank you.
Okay.
I have a question about what specific operation the ALU is doing here. Is it just adding our offset from the immediate plus whatever our current address is?
Correct. So the LU, here, it doesn't add function. So again, if we look at the table here, store instruction, LU operation is going to be 0, 0. Then that's going to be an LU for the LU function is going to be an add. So that's going to be a 0, 0, 1, 0. So that's what we're going to be doing here, offset and plus the base address that goes through here. That's get added and become your target address as the output. So yes, that's going to be an add function. Okay, so so let's annotate this real quick with actual terms. So we got X29 going through there, right? We got X9 going through the read register 2. So we have here, I'm going to write it actually here. So we have the offset there, right? So again, this offset came all the way through here. So it would be good if you want to write it here as well. Due to time, I'm just going to write it here on the bottom. And then we have here our base address. It's going to be added there. Base address plus the offset. What else do we know? That becomes our target address here. That's our output, right? So base address plus offset, that's our target address. Can somebody tell me what's going to be LU control?
Will it be
0,
0,
0?
0, 1, 0?
Correct. That's going to be 0, 0, 1, 0.
Oh,
And what's going to be the LU up?
Would it be
0, 0.
That'll be 0, 0 correctly. Right. So again, also all straight from the table as I just show you. So now we have that information there. So let's go. Let's work in control right now. Branch, and we know that's going to be only a 1 bit at a 0 or 1. We know this is not a branch instruction. That's going to be 0. Then we're going to have. Are we going to go from? Are we going to read from memory? Is that 0 or 1?
0.
It's going to be 0 because we're not reading from memory. We're writing into memory. So that's going to be 0. Now, mem to register, that's going to be a 0 as well, because as you can see, we did not highlight afterwards, right? This part here, this stage is the write back to register. So that's going to be a 0. So we did not go from memory to register. And then we're going to be, this is going to be a 1 because we did write data into memory. How about LU source? What's that's going to be?
1.
Yeah, it's going to be a 1 again, because this is the one selecting the multiplexer. And how about for rec write?
0.
It's going to be a 0 because we did not write back to register, right? So we did not write anything to register. Are we missing anything here? Our opcode goes here, right? There. We know that it's going to be PC plus 4. Right there. And again, don't forget to highlight the top. I didn't do it right now. I just did partial, so for time purposes.
I think we're missing the data from read data 2.
Oh, we can do that too. So X9, they just say that's going to be a 3, right? So that 3, yep. They said that's going to be, I'm going to say X9 is equal to 3 right here. So you can see where that 3 is coming from, meaning that 3 is being held, the value of 3 is being held in X9. So I wrote it here in this line here, right? So we know that now we just went to this target address, that's whatever that's going to be, and we're going to write 3 in that address. Questions about the store instruction?
Could you repeat the value of ALU source? What determines the value of it?
Yes, so remember the LU source is going to be either 1, if it's in this case, it's going to be a 1 because the input that's getting this offset that's going through here is what's needed, right? So that's why that 1 is selected as a multiplexer. So this LU source is first the LU source is going to get that 1 bit, and then it's going to communicate this multiplexer indicating it. You're going to get an input from whatever input you get from the 1, that's going to be the offset. So they're going to use that input, we're going to activate this path, and we're going to send that offset to the LU. For the ART type instruction, it was 0 because it was getting this read data 2 directly to this multiplexer and not the offset, right? So that ART type instruction, store instruction. So that's why it returns it.
Thank you.
Any other questions? All right, let's see what's next. Load instruction, right? So similarly to how the store instruction behaves, let's do some highlighting. So PC here, we're going to do the same, right? We're going to go over here. There's always opcode goes to control. Do we have an RS1 in load? So I have the load instruction at the bottom. Here, yes.
Because it's an immediate
Uh-huh.
instruction. So
About for do we have an RS2?
No.
Here, no. That is correct. Do we have an RD?
Yes.
Yeah.
We do have an RD. Okay, so right now, how about this part here? Where do we stop? Do we go down? Do we continue?
you should continue.
Mm-hmm. We continue because what do we know about load instruction? It has an offset, just similar to the store instruction, right? So we need to send that, we need to calculate the address to be able to know where we're going to retrieve the data from. So we know that's going to go through here. So that's going to be our offset going through there, right? And we don't have our read data too, right? We don't have a register 2. That's not highlighted here. So we have an RD, right? So this RD, we know we're just going to write back to register. And then we're going to read data from read register 1. That's going to go through here, right? So that's going to be our base address, which is x29. Offset plus x29. So that means that there's going to be an add function sitting there, right? So, and then that's going to go to divide to this place over here, which is going to read the address where we're going to retrieve the value from, right? Then we're going to read the data. We're not going to be writing data. So we're going to read the data from this address, and then we're going to send that to this multiplexer. So this one is going to be activated, and we're going to write back to register. As a reminder, load instruction is the only instruction that goes through all the, is doing something at all the 5 stages. We write data into this register. Did we miss any highlighting? Besides the top, please do the top. You already know it's the same one as the R type instruction for the PC plus 4. So there's no nothing different there. Okay.
I do have a quick question.
Are
you able to quickly show like which ones the fetch, execute, and decode, and then the read and the write steps, or like, yeah.
Yeah, so you said to show you the fetch and the decode. You mean from PC all the way over here? You want me to show you that again?
Yeah, at least like the fetch, execute, and decode, because I can the read and write are like in the data memory, but the fetch and execute, the decode, I don't. There's not a clear divide for my.
Yes. So for the fetch, always remember this happening from the PC to the instruction memory right here, right? So we're going to fetch the instruction. That's why I said read address So if you read the address, we're going to retrieve the instruction from the instruction memory. And then once we retrieve the instruction memory at that specific address, then we get to the decode side, right? So the opcode goes here, RS1, and so on. These happening, these buses here, and these races, this is where the decode is happening, right? So now we're decoding, meaning that these are the races that are being used, and the value within the register starts located there. The execution stage is happening at this LU stage here. So always remember the execution stage is where the operation, the functions are happening, the arithmetic functions are happening at the LU stage. Accessing memory, of course, where data memory is located, and the write back to register is just this piece right here at the end. Just this, honestly, this multiplexer and this line is the write back stage because it's writing back to register, back to the registers here. Does that answer your question?
Yeah, so just like the branching is where like the branching and then the control and then the registers portion, except maybe like the write data portion. That's the decoding part, right?
Correct. So this whole, you can say this part here is the decode.
Okay.
Yeah.
Thanks.
No problem. Yeah, pipeline does actually a better job breaking down the 5 stages, but because it has pipeline registers and buffers, and it does look more constrained. All right, so let me cancel that. Yeah, we're gonna keep that, and then we're going to do some annotations, just like we did for the other ones, so we know what's happening at each stage. So we got opcode, of course, going to control. We have over here read register 1, so that's going to be our x29 because that's our base address. So then we have here our RD. So I'm sorry, yeah, so that's our RD, that's our x9. So then afterwards we have our offset, right? Going through here, offset, and we're going to, I'm just going to write it here. And then of course the highlighting kind of helps where the offset is coming from. And then we also know we have a base address here. And then of course that becomes our target address. I'm gonna write it right here. Okay. So this becomes our target. I'm gonna write TGT as target. And then our final value, say we just got the value of, I don't know, 5 goes through here. That's what we retrieve from that from memory. That's gonna get written back to register. So X9 is gonna be holding now the value of 5 in this case. Okay. So let's look into the control. Branch, that's kind of should be a given, that should be a 0. How about main read? Is it gonna be a 0 or 1?
1.
It's gonna be a 1 because we're reading from memory this time around, right? So you see that line goes over here because to data memory. So it's telling data memory, hey, we're gonna go to that address. We're gonna retrieve a value from there. We're gonna see what's allocated there. Memory to register, is that 1 or 0?
1.
Yeah, it's gonna be a 1 because we're taking the value from memory and we're writing back to register. How about LU? LU always gonna be 0, 0, right? Based on the table. So if we copy that again, if we're gonna use the LU control, what's gonna be control?
0, 0, 1, 0.
Correct, that's gonna be 0, 0, 1, 0. How about mem right?
0.
That's gonna be 0 because we're not writing into memory, so that's why it's a 0. How about LU source?
1.
Be 1 because the multiplexer is 1 because the offset is going through the multiplexer. And how about reg write?
0.
Reg write is a 1 because we're running back to register. See that here? As long as you have an RD, you're gonna write to register. So because we wrote to register, that's a 1 in this case here. Questions? Did we miss
I
any
have a quick
annotations?
question.
Go ahead.
So just to be clear, so whenever the instruction goes through the pipeline of the write register, like for X9, it's assumed that X9 is just it's not going anywhere else. It's gonna stay there and wait until we receive the data, which is the write data. And then it knows, okay, we're putting 5 into X9 and that's that in the registers.
Correct.
Okay, and then reg write would be 1 in that case because we want to write into a register, which is X9. Okay, that makes sense.
That's correct. Yeah.
Okay.
Yeah, so again, if this reg write is 0, then pretty much control is telling the registers hardware that we're not going to be writing to this RD, and that's not the case. Okay. Here. These are more annotations for you. So this is pretty much where the immediate value goes through. To make sure offset, that's becomes your offset here. Okay. I think we got this one. Yeah. It's always good to double check that you have lighted everything. Again, don't forget the top here. It's always good to check that. Branch. When branch is taken, this is this one, of course, going to be looking a little bit different than the current ones that we had seen. So this one here, again, PC, structured memory, typical, right? We're going to do the fetching. I'm going to read the address here, provide the instruction. What do we need for a branch? Do we have an RS1? And again, I have the instruction back down here. Right, so if you look at the instruction, we have an RS1, we have an RS2, right?
Yeah.
Do we have an
Because we would do
RD?
the comparisons for that.
Correct. Do we have an RD?
No RD.
No.
All right. How about this part here? Do we continue or do we go down?
We go down.
Go down.
Okay. We go down to LU control. We know we have an RS1, we have an RS2, and typically if we can, actually, I'm sorry. Should I say no? We do not go down. I'm going to leave it right there for now, and I'll explain that in a little bit why we don't go down. I'm going to stop it here. We have an RS1 goes through here. We'll have an RS2 that goes through here. Right. So the 0 is going to be selected. So we have the value of RS1, the value of RS2 is going to be here. We're saying the branch is taken. So if you see the condition here, the branch is taken there. So something else to highlight, this is going to be highlighted. This line right here on the top. Okay. So if that one is highlighted and you need something else to add, so this is going to be highlighted too, right? Shift left 1. You see where this line is coming from? This is why we don't go down. So now this input, instead of going to the multiplexer, we go all the way up. Now this add instruction is having the value of PC in the current address plus the offset. So this output here is going to be PC plus offset. The shift left 1, that means that 2 square. So we're going to pretty much add in about 4 bytes. So we're making space here to be able to do the corresponding calculation of the offset into the program counter, adding that to the program counter, making sure that we have the correct, and we jump to the correct address based on that calculation. But before we go up there, because you can see now this multiplexer has 2 inputs, potential inputs. So at this point, we don't know if the branch is going to be taken or not, right? So we are at the decoding stage. we send the value of RS1, we send the value of RS2 to the LU, but we don't know if the branch is taken or not yet, right? We haven't made that decision. So that's why this multiplexer now has two different inputs, PC plus 4, which we have been doing that for all the other instructions. And then we're going to add the offset to the PC, which are the value of the PC, the address of PC, going to be here. Of that instruction is going to be plus offset to be able to calculate to go to the next, to jump to the next instruction. Because we're saying the branch is taken, right? So we're making the assumption that when you, what function is happening at the LU, by the way, for the BEQ or any branch?
Subtraction.
The subtraction. So subtracting the value of x9 and the value of x28. So we're saying if it's equal to 0, the value holds. I mean, then the condition is met, and then of course the branch is going to be taken. Because the branch is taken, we're going to say that yes, that's a 0, and we're going to activate this AND gate. So you have 1, 1 here, you have an output here, and this is 1 is selected. Hence, 1, 1 is equal to 1 for an AND gate, right? So this 1 is selected, so this input does not get selected, so it stays there. And of course, this is the new value of the PC plus offset goes through here. And definitely not good with my right hand. All right, so what else do we do? We know the branch is taken. We already know that with 0, it's saying as this AND gate is activated. So 1, 1 here. Is there anything else that we need to highlight? What do we do here?
What was the question again?
What else do we need to highlight? Is there anything else we need to highlight? And what do we do here in the data memory multiplexer area after the LU?
Do we need to highlight from the ALU result to the multiplexer on the right?
You mean over here?
Yeah, from ALU result to the multiplexer.
We do not. So only we need to know is when you have a branch instruction, again, if it's going to be taken or not. If the branch is taken, then we know that's the outcome of 0. So it indicates it's going to activate this AND gate here, right? So actually, I'm going to highlight this part here too. Again, it's highlighting this line. It's not highlighting mem read. Again, it's not highlighting mem read. It's just highlighting the branch here. So again, you're going to have 1 on 1. It's going to be 1. So we know the branch does not touch data memory. And we do not write back to register either. So if you see there's no write register, there's no RD activated. So that's why we don't touch any of these. None of that, it gets highlighted at all. All the highlights that we need to do, we already did it for a branch instruction that when the branch is taken. Okay, so let's do some annotations. All right, so we have the annotation here. Let me see, we're gonna go here and steal some, so I can copy paste that. All right, so we got X9 register. We're using that as an RS1. Here it's gonna be your X28. Right, so that's gonna go through there. Okay, so we know that here goes the value of X9. So I'm gonna see X9 value goes through here. Then we have here, it's hard to, it's a lot going on, but we're gonna say X28 value goes through there. And then that pretty much we subtract those two values and then telling us that 0 is gonna be used. I mean, so the 0 is the output, means that branch is taken. What's going to be our branch value for control?
1.
1.
It's going to be 1, right? Because we have a branch instruction. So So in this case, then how about memory?
0.
That's gonna be a 0. How about mem to register?
0 as well.
That's gonna be a 0. How about our LU up? Oh, I didn't write that.
Zero one.
It's gonna be 0, 1. So what's gonna be your mem right?
0.
That's gonna be a 0
0.
because we're not writing to memory. How about your LU source?
0.
0.
That's gonna be the 0 because the 0 is being used in the multiplexer. How about reg right?
0.
That's gonna be also 0 because we're not running back to register. So you can see how many zeros branch be getting, right? Because it's really just what we're doing is trying to we're gonna branch or not, right? So that's what we're gonna do. What's gonna be your LU control?
0, 1, 1, 0.
That's got 0, 1, 1, 0. That's gonna be your LU control. Why? Because we're doing a subtract function in this case here. At the LU stage. We know that opcode goes through here, right? And then here is going to be, where should I write it? I'm gonna write it here. PC plus the offset times 4. That's gonna be how we're gonna jump to the next address. Am I forgetting any? I mean, for the sake of explanation, I'm gonna write it here. We have a PC plus 4. That's still into account, right? It just that the output still was here. This was the output. So after the add sum here, that's what's selected because the branch is taken. And yeah, I think we pretty much annotated everything. Questions?
Will we ever learn any other branch statements besides the equal one?
The all the branch conditions follow this path.
Okay, so it would just basically be the ALU control that would change how it would be. Instead of subtraction, it would be something else like addition or whatever, essentially.
Correct.
Okay.
But then pretty much everything else, the path is pretty much the same.
I have a question about what goes on at the the shift left one circle. Is that just taking whatever immediate we get from the immediate generator and just shifting it left one so that we can add the PC counter and sort of like how you would do with an array and an offset?
Pretty much, yeah. So we're just taking the immediate value that goes to the shift left, and the shift left one is pretty much. If you guys recall your the SLI instruction, it's kind of doing that. So in this case, it's 2 to the I. So 2 to the 1 is 2 squared. I mean, in this case, it's 2 to the 1, so it'll be 2. But ideally, it should be showing 4 bytes here to be able to calculate your offset. That's pretty much. It's multiplying your the value of your offset times 4. Hence where the 4 came from here. And the PC, of course, remember the PC is coming from here by itself. So you're adding that PC plus the offset times 4, whatever that's going to be, it's come through here. But that's what the shift left does.
I thought shifting left by 1 only multiplied it by 2, though. You're saying it multiplies it by 4 here?
Yeah. Yeah. And that shift left 1, we should not see that in the pipeline. It should be different.
I have a question.
Mhm.
You said shift left 1 shouldn't be in the pipeline and it should be different. Can you explain that a bit further?
No, so keep in mind that when we're looking at a single cycle data path, that's it's not practical for today's machines. So they are. So again, we're pretty much just processing one instruction at a time. Compared to a pipeline version, we have multiple instructions at the same time. You should have about 5 instructions pretty much filling the pipeline. So the reason why, of course, we're showing you a single cycle data path is for you to understand how each instruction gets processed through the CPU, and the same principle that we're looking at here, we use that for the pipeline version as well. But then when you look at the pipeline data path, there's way more going on, which makes it more complex to be able to be highlighting and annotating within the pipeline itself. That's what I'm referring to.
Okay.
Yeah, then of course, if you're working with floating point for format and things like that, using type of data size and all of that, and it all depends of the ISA itself, the version of the ISA, but in practical, it follows the same trajectory for the different type of instructions. You good?
Could you quickly go over how you explain what goes on in the ALU box?
This part here?
Yeah.
Yeah, so again, the value of X9, whatever value is in X9, the value of X28, they both get subtracted. So the subtract function happens at the LU, that's why the 0110 is here. And it's pretty much indicating if this is equal to 0, then the condition is met, so the branch is taken, as that's the condition we're showing here. So that's why we activate this line of the AND gate. We already get that activated here for the branch. 2 lines it gets activated, so that's why that activation happens for the branch. If the subtraction is not equal to 0, then the branch is not taken, and there's nothing else that needs to be done.
Thank you.
I do have a question about the immediate generation and then the instruction branch on the bottom.
Okay.
Would there have to be a multiplexer in there or no?
This part here?
Yeah, like would that require multiplexer or no? Or is that the 30, 14 to 12 going into the ALU control always?
It always goes to control.
Okay.
The reason I did not highlight that is because I want you to concentrate mainly on what we need, to execute the instruction. But some part of it does go to control, yes. That's why multiplexer is not needed.
Why is that the case?
Which part?
The why 30, 14 to 12 specifically? Is that what's the purpose of that?
Again, that's based on the design, how they designed the instruction formats for the RISC-V ISA. So that's why we're indicating those numbers is just indicate, well, any immediate value or function, immediate value goes through here. Of course, function-wise, it goes through here to LU control to help with indicating what type of function is going to be done for the LU.
Okay, I see. It's like the func 3. That the 14 to 12 is the func 3, and then the 30, I guess is just 30 at that point.
Correct, but keep in mind that it also needs to be general enough for all the different type of instructions.
Yeah.
Okay, so again, we're using the same exact data path, right, for multiple instructions, which have their own format. Yeah.
All right.
All right. You have a question? No, yeah.
Oh no, I just said thanks.
Sounds good. Let's do the last one. Go ahead.
I have a question. So on the last one, I was still a little confused about what exactly the immediate is.
Let's see, I can show you this. You see this immediate part here?
I do.
Yeah, so this part of the immediate, that's what travels through the data path in that area. So for example, when you look at I type of instruction, the immediate is going to be your offset, or it's going to be your constant. So anything any value that's not held in a register is going to be your immediate. So for your branch instruction, your immediate here, right? The immediate generator is going to go through here to calculate the address that you need to jump to. So that, of course, that's going to be a value. No, there's no register traveling to here. So that's why the immediate generator needs to, it's going to convert that to the format that the data path accepts. Because if you look at the immediate here, they are not the same. All of them are the same size for the number of bits. So the immediate generator pretty much standardized that for the data path. Does that make sense?
Mm-hmm.
Yeah, so that's where the immediate comes for. This for the branch instruction, also for the other instructions as well. Alrighty. So let's look at the same exact instruction, but what happens when the branch is not taken? I'm not going to highlight everything. I'm just going to show you same thing here. So you know you have to highlight all of that. Oh, terrible. To go into control. We know we have an RS1. We know we have an RS2. We know this part here goes to the, as an immediate generator, goes all the way up to calculate the next address that we need to jump to. It goes through here. Our PC also travels here, right? That needs to go through there. Also, PC plus 4 needs to travel through there too, right? Because we don't know if the branch is taken or not. We know because I told you it's not taken, but the hardware doesn't know yet. So when you go to read data 1, read data 2, series selected, output here. So you got X9, X28 condition. That means that when they get subtracted here, it's not a 0 outcome, right? So what do we do? It means that the branch is not taken. So
We
what
have
do we
to
do
execute
next?
the next line, right? In like the RISC-V code.
All right, you pretty much at that point, because the branch is not taken, in the CPU, pretty much what happens is the BQ instruction just travels across the stages, nothing's happening, and just exit the data path. And then the next instruction is being fetched over here. So let's annotate that so we know. You can see the difference. And again, make sure you annotate everything, even highlight everything, just like we did in the other one. I'm not going to do that first here. We know that's going to be, so here, this is going to be, the output is going to be PC plus 4 because the branch is not taken, right? So that PC plus 4 that came through here, that's going to be 0. Actually highlight that 0. And then we're going to use PC plus 4, right? What else we need to annotate? That we have not annotated. This does not get highlighted, so we leave it like that. So we can say, of course, X9 go through there. The value of X9 go through there. The value of X28 also goes through here. Right there. Oh, that'll be. Okay. Any questions? Any other questions about branch not taken? That's really the simplest one because you know this. If it's not taken, then there's nothing else to do.
Everything in the control remains the same, right?
Yes, everything in the control remains the same. So pretty much that's going to be 0. Let's do that real quick so you can have it. That's going to be, so you can do the thought process. Oh, I don't know what happened to my 0 there. Huh. If we're going well. All right. I'm going to take that to 0. So again, mem read is going to be 0, right?
Well, branch would be 1 though. It just wouldn't be ANDed with
That is
the
correct.
0.
That is correct. Yeah, so that's going to be a 1. It's just that the other side was not activated, so that's why AND gate does not get activated there. To register, that's going to be a 0, of course. How about your LU source? I'm sorry, the LU up.
Still going to be 0, 1.
Correct. Mem, right? It's going to be 0 because we're not
0.
running into memory. How about your LU source?
0.
It's going to be 0 because that's our switch going there. And our reg right is going to be a 0, right? We're not running back to register. LU control is going to be 0, 1, 1, 0. Okay. Any questions about any of the instructions?
So because we're not activating the memory write and then that multiplexer, that memory to register, those won't like execute at all. Like it'll
Correct.
just stop right there. Okay.
Yeah, it will just stop at the LU stage.
Okay. So it won't go through it. Okay. Got it.
Mm-hmm. Yeah, the questions, add, famous R type instructions, store, load. When the branch is taken, branch is not taken. All right. No questions at all? So again, as a reminder, it's good if you practice yourself without, now you have the notes. Do highlight everything here, right? So you have the actual highlighting. So this gives you, now you understand better how these instructions travel through the hardware. At least for a single cycle data path, and what happens with where the opcode goes. Why is this format important, right? So we have the opcode, the RD functions, and so on. Why they're broken down into different fields for each of those instructions is because each of those fields do travel to the different parts of the hardware, so they have their own function in that regard.
I have a question.
Mhm.
So for each of like the branch and the mem read and the mem to reg, we had to denote the value, but for the opcode you just wrote OP. So do we not need to know the opcode value?
Not necessarily, no. As long as you say opcode goes through here, it's more important for me to actually know what happens afterwards, right? So the output of the control helps you understand what part of the hardware is going to be activated based on the type of instruction.
Okay, thank you.
I have a quick question.
Mm-hmm.
I thought we learned previously that the opcode is 7 bits, but it seems like it's 8 in this case. Or maybe I'm just confusing that up.
No, it's fine. I get that question all the time. So yeah, so the opcode is 7 bits for the control. However, remember that LU up, it needs to be 2 bits. You see how this wire is extra thicker than the other ones? Can you see that?
Yeah.
Yeah, because of course it's an extra bit. It cannot be 1 bit because of the number of functions, right? So that different type of instructions and the number of functions that different type of function that needs to go through the hardware.
Okay, so we're now saying that the opcode is 8 bits because we need that extra bit for the ALU to choose.
I would not say that. No, the opcode is always 7 bits. It's just the output of the control is going to give you 8 bits to be able to communicate with the data path.
Okay. So it goes to the control, has some actual processing involved with the opcode, and then you get these bits out. Got it.
Correct.
Okay.
Yeah.
Oh, that's right. I actually remember that from the lab now. I remember. Thank you.
Okay. No problem.
I have a question about the table with the ALU opcodes and the operations on it.
Mhm.
Yeah, that one. Will that be provided on the exam?
No.
Okay.
For exam number 2, I do not provide any tables whatsoever or formula. So, and then if these show up in the exam as I do provide the full data path, then of course you have to annotate it and highlight it in that case.
In those annotations, will we be required to like right there on the instructions where it specifies which bits specifically out of the instruction, will we be required to memorize that too?
Are you referring to like where like X28 is going through here?
Not where it's going through, but like the 19 through 15. Will we be required to like memorize exactly which bits are for which one?
Not necessarily. Again, I will just provide the empty single cycle data path. What I mean empty is the 19 and 15 will still show up there. You just need to know the X28, right, will go through this bus here.
All right, perfect. Thank you.
I do actually, for like a test question, do we always have to write the instruction, like highlight the instruction line? Because I know for like the immediate generation ones, like we skipped that instruction path, although like the ALU control still does receive it. So should we like include that as well, or
which part are you referring to? This part here?
The split between the immediate generation and then the instruction 30, 14, 12.
If it is an RTAP instruction, you leave it empty. So if it is a load, for example, the store instruction, you see how we highlighted that here?
Yeah.
Then you just do that, yeah.
Yeah.
But if it is an R-type instruction, then just do it down here, yeah.
But wouldn't the ALU still take in the 14, 12 bits of a store instruction, or?
Correct, yeah, it would. But again, if you do highlight both, that's okay with me. You're not gonna take any points off. But this part here, for a store instruction, I want to see that you understand that that's how it works.
Okay.
Yeah.
All right.
Now, if again for an R-type instruction, make sure you do not highlight the immediate generator.
Okay.
Yeah.
Cool. Thanks.
So pretty much what if you see, I'm trying to highlight the stuff that we really need for that that instruction, even though I didn't highlight the LU control for the other ones.
Also, what is the immediate generator? Is it like some sort of like combinational circuit that creates a 32 to 64 bit thing, or what?
Yeah, so the immediate generator is another part of the hardware within the data path that it regulates the number of bits within the of the immediates, right? Because you look at all the immediates of the different type of instructions, they're all different number of bits. So the immediate generator pretty much formulate that, okay, this is going to be now a 64-bit, and then we can send that either to the add hardware on top, or we're just going to send it to the LU, as that's the typical number of bits that they are used to handle. Instead of getting like 3 or 5 or 7 or so on, 12 it's pretty much standard.
Does it just take in like the whole instruction, or is it just like only the immediate portions of the instruction?
Just the immediate portion of the instruction.
Okay. And that's just determined by what?
What is determined what?
Like, because the immediate portions of different instructions can appear in different parts of the instruction. So the immediate like portions of an instruction can sometimes appear in different places depending on the instruction. So it's like, how does the immediate generator know what to pick?
Well, it's So when it comes to the immediate journal, pretty much taking all the immediate values, it goes through there, right? So when we look at a single cycle data path, there's no other place the immediate can travel through, right? So anywhere else, the immediate has to go through here. Any immediate value has to go through there. So it pretty much takes all the bits, all the immediate all the values. So if it's 12 or so whatsoever, and convert that to the bits that the data path is. It is. If it's a 64-bit, of course, it's going to be a 64-bit, and it's going to go through the LU. But there's no other way. There's no other parts of the hardware that the immediate can travel.
Okay.
Mm-hmm.
All right.
Yeah. And then this is 449. So this is where we end the practice. If you have more questions, just please, email me or join office hours, or you can ask me on Monday. And Monday, of course, we'll continue pipelining and so on. So have a good weekend.
Isn't Monday Veterans Day?
I'm sorry. See you Wednesday. Yes. Have a good long weekend.
Have a good day, Professor.
Have a good weekend.
Yes, well.
Have a good day, Professor.